Okay, thanks a lot. Thank you everyone for being here. So as the title suggests, I'm going to be talking about some machine learning strategies that we're using to try to find kind of a better way to analyze data and approach the problem of deep brain stimulation, specifically with regards to Parkinson's disease, using kind of these machine learning based techniques. So just to kind of signpost my talk, I'm going to start by just going with some really brief background about Parkinson's disease, specifically kind of the features of the problem that we care about, and then a brief background on what neural networks actually are, just to make sure everybody's sort of on the same page with kind of the vocabulary as we get into the actual work that we've done. From there, I'm going to talk a little bit about actually modeling real patient data. I'm going to talk about some of the challenges, what our objectives are with that, as well as the strategies that we actually use to accomplish that. And then lastly, we're going to look at some attempts that we've made to actually generate adaptive controls for deep brain stimulation using computational modeling. So to start, I want to just briefly touch on the key characteristics of the problem of Parkinson's disease that we care about. As you all probably know, Parkinson's disease is a degenerative disorder that causes tremors and a host of other symptoms in patients. One interesting thing about Parkinson's disease is we know what the cause is. It's a death of dopaminergic neurons, but the full mechanism, the full pathways in terms of how it actually influences and generates the symptoms in patients is not fully understood. And one reason for this is that a lot of that activity goes through the basal ganglia, which is a very small region of the brain and not very easy to access. So the exact pathways can be difficult to actually measure, describe, and understand. That being said, one thing that we do know is that if we look at the subthalamus nucleus and we look at local field potential readings, we see elevated activity in the beta, what we call the beta band or the beta frequency range, which in this case we talk about as being between roughly 15 to 35 hertz. The reason that we look at this, or the reason that we care about this, is because one of the primary techniques for treating Parkinson's disease, especially when pharmaceutical methods like levodopa stop being as effective, is deep brain stimulation. So we insert an electrode into the brain, we apply a high frequency stimulation, usually in the range of about 130 to 150 hertz, although there can be some variation. And it's been found that this actually helps treat the symptoms. But again, interestingly, because we don't fully understand the mechanism of Parkinson's disease, we don't fully understand the mechanisms by which this deep brain stimulation actually alleviates those symptoms. However, there's some correlational evidence that suggests that what it might be doing, or what one cause of this deep brain stimulation is reduction of this bursting behavior in the beta band. So the way that we usually look at this is we actually look at the power spectral density from the resulting LFP reading. So we look at the frequency response of this local field potential. And what we're looking for is to see if we can decrease the elevation in that, if we can get rid of sort of the spike in the beta band behavior. So an example of this is kind of in the figure that you see here. The blue curve is something that we might see as a bursting behavior, where you do have this peak that's in the beta frequency range, whereas the red curve, we don't see that same bursting behavior. So we wouldn't look at this as an example of bursting. One reason why we look at this specifically is because voluntary movement doesn't show this same elevation in beta frequency behavior. So it looks like it's actually associated with pathological behavior in Parkinson's disease. So DBS works pretty well right now. And one question that comes up sometimes is, if it does work, why are we spending time studying it? And the answer to that is really twofold. The first is, as I mentioned, we don't totally understand how it works. So of course there's academic interest in understanding better the mechanisms by which we're actually treating the human body. But the other is that because we don't understand how it works, it's not a very efficient process. And it's not efficient on two levels. The first is that to actually set up deep brain stimulation for a patient, the patient has to go through a manual tuning procedure with a technician, where they'll actually adjust the frequencies and the amplitudes of the stimulation to find parameters that best work for that specific patient. And this is just it's somewhat of an unwieldy process. The second reason is that because we don't really understand how it works, deep brain stimulation is either on or it's off. And that means that you're putting a lot of electrical current into the brain when you have it on, and it's not very efficient. We are maybe overstimulating at times or understimulating at other times, and we don't really have a way of adapting or controlling that with kind of the current conventional way that we do deep brain stimulation. This has a couple issues. One is that batteries have limited lifetimes. Another is that patients' physiologies can change on different timescales. One way that it can change is simply over the course of the day, since these patients are also on medication, they can actually experience sort of overstimulation from deep brain stimulation, as they'll get these dyskinetic effects from sort of the interaction between the DBS and their medication, while at other times of day, those effects aren't as pronounced, and it's more just mitigating the bradykinetic effects from Parkinson's disease. And of course, as the patient continues to age, their underlying physiology can change as well. So these are the kind of core issues that we're trying to answer with this. Like I said, because it's a very difficult area of the brain to kind of look at and to make really conclusive, definitive statements about, we thought that a good approach to this would be, instead of trying to find the specific how and why, look at it from a broader perspective of, can we understand something about the data that we get and use that data to say something intelligent about the system? And to do that, we turned to machine learning, and specifically neural networks. So just a very brief overview of what neural networks actually look like. You're going to have your input data. That input data gets passed into what we would call a hidden layer, and we'll usually have one or more hidden layers in what we call a deep neural network. In that hidden layer, we're going to first pass it through a linear transformation, where we're going to do, looks like my plus signs are missing here, but WX plus A, kind of a standard linear transformation. But then the key thing in any neural network is that we're going to pass it through a nonlinear transformation as well, which essentially allows us to map our inputs to the outputs in a nonlinear fashion. So everything that we do in this talk is going to be based around this idea of utilizing slightly different architectures for neural networks, but they all have the same basic structure. We have an input, we map it through several hidden layers to an output layer. And just in terms of these arrows, what we're showing is that one nice thing about neural networks is they have a very straightforward training method. You have a forward propagation step where you pass the input through everything. And then to actually train the network, we do a back propagation where we kind of exploit the chain rule to actually update the weights of all of the matrices in our hidden layers and in our output layer. So we update those weights and those biases to find the ones that best fit the output data to the input data. So based on this, we wanted to start by first looking at some actual patient data and trying to see what we could say about that patient data by examining this sort of data that we could take in. We were very fortunate. We've been in talks with some colleagues up at UC San Francisco at the STAR lab, and they very graciously shared with us some data they had collected from PD patients who had received these surgical implants with deep brain stimulation. And there were a couple different things we wanted to address with it that we found when we started working with this data, especially compared to sort of, I guess, more traditional machine learning problems. And broadly, I would say there were two different issues that we really wanted to address. The first is what I would kind of say is an overfitting issue, which is always kind of an issue whenever we're doing any sort of machine learning strategy, but we found it was especially an issue here. And the next is benchmarking. So with overfitting, there were sort of two main issues that we identified. First is that you have different patients, and every patient has a different physiology. So this can be as simple as just different kinds of readings in the local field potential, different responses to actually having the deep brain stimulator implant placed in the brain, because it might be in slightly different locations relative to the STN, or the progression of their PD might be slightly different, things like that. The other thing is that we have a relative sparsity of training data, especially compared to sort of the big data science problems like image identification, where you can have millions, not billions of training points. Here we had a relatively confined data set that we could work with. So with both these things, we wanted to make sure that we weren't going to generate something that only worked in a very specific application or for a very specific patient. And that our solution provided some sort of a sufficiently general approach that it could work for a new patient that you hadn't seen before, that hadn't been part of your original data set. The other issue was one of benchmarking. And the first question we asked was, what sort of is an appropriate benchmark for comparison for this? What is something that we can look at as evidence that our machine learning approach is doing something useful? And that tied also into the question of what an appropriate objective is as well. So I'm going to answer that last question first. As I mentioned before, one thing we see with deep brain stimulation is that there's this elevation in the beta band. And in a very coarse sort of way, we can say that what we're interested in is eliminating bursting in this beta activity, or in this beta frequency range. So what we decided was, let's take the data that we have and we'll classify different power spectral densities that we get out of our local field potentials as either examples of bursting. So we either see a burst in this window where we have an elevation in the beta band, or we see it as no burst in that particular window. So we'll classify them as one of the two things. And then what we decided we wanted to do, what the sort of ultimate objective was to say whether or not we should expect in a subsequent window to see a burst or not see a burst based on some current window or some current input stream of data. And this had to be receptive to both the current state of your system, which in this case is the current power spectral density of the local field potential, and also subject to whether or not we're actually stimulating our system. So whether or not control is actually turned on or off in the next step. Because again, just to bring it back to what we're actually trying to do here, we're trying to see if we can create an adaptive strategy for deep brain stimulation. So what we want to really see is whether we can make decisions about whether to turn on or off stimulation based on what's going to happen in the next time window. So for example, if we look at this and we see that it is likely that we're not going to see a bursting activity, even if stimulation is turned off, that can be an indicator that we can just turn off the stimulation and not use it in this time step. And then when we see that we need to turn it back on to maintain kind of the state where we don't have a bursting behavior, then we can turn back on that stimulation as well. So that was what we kind of decided to do in terms of the objective. In terms of benchmarks for that, we talked about a couple different ones. One was sort of a null hypothesis benchmark, which was essentially that nothing changes from step to step. So if it's bursting right now, it's bursting in the next time step. And the other one we kind of thought about was a Markov decision process, where we use the conditional probabilities of a burst versus a non-burst based on the current state of the system. But the main issue that we needed to address was this issue of overfitting. And the way that we decided to go about solving this was by using an autoencoder, which is a specific type of neural network. Now, the idea behind an autoencoder is that we actually extract key features of the network by trying to reconstruct the original signal, but passing it through a bottleneck, where you only have maybe 2 to 3 outputs for one of the layers of your network, which essentially projects the original data onto a smaller space mapping. This can be seen if you're familiar with PCA. This is a very similar process to PCA. The primary difference is that in PCA, it is a linear mapping, whereas an autoencoder actually allows us to get out a nonlinear mapping of the data. And again, one of the reasons we chose it was because we felt it would be a good way to address some of the overfitting concerns that we had, because we were sort of just extracting key information rather than just directly mapping from local field potentials onto it. So using this autoencoder, the first thing we had to do was we had to build the autoencoder. So we trained the autoencoder on our data. And then once we had that autoencoder, what we actually wanted to do was create a calibrated predictor. And what I mean by that is not just a predictor that said, I think there's going to be a burst or not a burst, but we wanted something that was going to be more useful to, say, a technician that might be working on this problem or working with a patient. And so what we wanted to do instead was to give a likelihood that a given burst was going to occur or not in the next time window. So a probability of that burst occurring between a likelihood of 0 and a likelihood of 1. And again, based on both the current state of the power spectral density, as well as whether or not we turn on or off stimulation in the next time step. So the good news is that when we did this on our training data and we compared it to the validation data, we found that we were actually able to get what we think are some really promising improvements over the two benchmarks that we talked about, those Markov decision processes and our kind of, again, quote unquote, null hypothesis. There were a couple different areas that we were primarily interested in. The biggest one, of course, was sensitivity. We wanted to make sure that we were catching when a burst was going to occur and we were correctly predicting true positives. But the other one was we didn't want to just, if we always turned on stimulation, we could always predict that there's a burst and we would have 100% sensitivity. So we wanted to also make sure that we weren't selecting for when there wasn't a burst. And so we were also interested in the precision and balanced accuracy of our predictor. And what we found was an improvement over the benchmark case for all three of those metrics. Also, kind of critically, we found that it maintained a higher level of performance as we extended out the actual gap between when we were looking at it and the result. So what I mean by that is, as we shifted this window away from the current state, you can imagine that if there's no time difference between the two, well, then our sort of null hypothesis is going to have 100% sensitivity, 100% accuracy, et cetera. But as we shifted away and we increased the time between the two windows that we were looking at, we found that our new model was much more robust to that than this kind of these benchmarks that we used, where you started to drift toward essentially random chance. The other thing is, like I said, we wanted to make something that was calibrated. So we also looked at the calibration of our model. Perfect calibration would be sort of if we were along this dashed blue line in our second figure here. So it's never going to be perfect, but we did find that we had a sort of nice correlation between the predicted likelihood and the true likelihood when we binned those likelihoods for analysis. So that was what we did with the real data, but we were obviously limited in a lot of ways by what we could do with real data. One big way that we were limited was, again, the sparsity of the data, but also the fact that we were only making descriptions of that data. We couldn't actually see what would happen if we actually tried to apply control to a data set. So for that, we had instead turned to computational modeling, which obviously gives us a lot more flexibility to try things and figure out what works and what doesn't. And here, we wanted to do something very similar, which was based on the current power spectral density, what is going to happen to the system in some future time step? And then once we've decided that, since it's now a control problem, let's select a stimulus to meet some arbitrary control objective. Now, with this, we also have an additional degree of flexibility where instead of just saying on or off for a control, we can do things like specify what stimulation frequency we actually want to apply. In terms of the actual design, we wanted to do something that was sufficiently flexible so that you could implement a number of different control objectives depending on what was appropriate to what you were trying to do. And also something that would be adaptive to, again, that changing physiology we talked about before, whether it's because of medication or just a disease progression in a patient. So the model itself was taken from sort of two papers by Van Albada and Robinson from 2009. And then the actual code that we used was adapted from a paper from 2018. The idea that we used in what you're about to see was we wanted to select a stimulation frequency for each window that we looked at so that the peak of the beta band was below some threshold with a certain probability in the next window that we looked at. So this became essentially a regression problem. And I want to note here also that we're still using our same autoencoder. So we trained this autoencoder on the real data. We're going to use that same exact autoencoder, and we're not looking at the full power spectral density here. We're passing that power spectral density through our encoder to get those extracted features, and it's those extracted features that we're actually going to use to make our ultimate predictions. So unlike the previous problem where we wanted to do something that was just descriptive, this is instead a prescriptive problem where we're trying to actually select a control stimulus. And we're going to keep updating our model and continuously train our model to respond to errors that it's seeing and try to match the values so that we're going to hit a specific probability Q. So the first thing we did was we wanted to look at it in a case where we held it at Q equals 0.5 and we didn't change any of the parameters in the system. This threshold might look a little arbitrary, this 15.781. The reason we chose that is because in the model that we used, that's actually the mean power in the peak of the power spectral density in the system when you use 130 hertz of conventional deep brain stimulation. So we wanted to use that as sort of a reference point for what we were doing. So using that, let me see if I can just minimize. Oh, nope, that was the opposite of what I wanted to do. I think I can just close it. So we did this first again with, we did 10 trials with this threshold and with this probability. And what we found was we were pretty able to quickly adapt to pretty close to our target. If you look at the figure at the left, this is the average frequency across the 10 trials. And then the darker purple line, the thicker line is actually the average moving frequency. So you can see it starts out too low, but quickly climbs into this range that's around that 130 hertz that we see in the conventional DBS. But you are going to see more fluctuations because we are trying to kind of keep it a lot more steady. With the conventional deep brain stimulation, you're going to see a lot larger fluctuations in sort of the moving average probability in the figure that you see it right. I will note it overshoots a little bit in these first 1,000 seconds of simulation. It's around, I think, 0.54 on average in these trials. And obviously, you can see that on a trial-by-trial basis, it fluctuates up and down. We found that it settles pretty much in the first 2,000 seconds, but the first 1,000 is kind of pretty good for seeing that we're getting behavior that we're pretty happy about with this. It's pretty consistent. We have it in a fairly narrow band across all the trials. All of them are able to hit pretty close to that 0.5 moving average probability that we're looking for. Now, this was only the first part of it. The second thing that we wanted to do was, again, make a system that was reactive to changes in the underlying physiology of the patient. So to model this, we actually varied the parameters with a certain period tau. And so just as a last thing, we did this adaptive deep brain stimulation with varying different parameters of tau and with, again, varying targets for the probability. So in the figure at left, we use this kind of longer tau of 5,000 seconds and a target probability of 0.4. And you can see really clearly in the blue how the frequency is actually undulating up and down with this period of 5,000. So our model is actually able to match the variation in the parameters. And when we get closer to sort of a state that might be considered an overstimulation normally, we actually drop that stimulation so that it maintains just the same performance instead of kind of overstimulating like you might see in the presence of medication or something like that. In the right, we just did it for a slightly faster period of 2,000. It's not quite as successful in tracking it. You can see that it's a little bit higher or lower, I guess, compared to the 0.6 it's going for. In general, what we're finding is, it's maybe not surprising that the longer the period is, the kind of better it is at maintaining that tracking. And we're still looking at kind of what the critical limits are there in terms of the actual speed at which it can do this. But those were sort of the key results. We're very excited about this. We're sort of just in preparation to submit right now. So it's all very, very fresh. But that, I'd just like to say thanks. And if you have any questions, please let me know.
Brilliant. Thanks very much, Tim. Are there any questions? All right, I guess I have a couple of questions, Tim. So just thinking back to the sort of last bits that you talked about. So this is like an adaptive control where you're reading in the data and your control scheme is updating sort of as you go, right? Am I reading that correctly?
That's right. Yeah. So every X seconds, we essentially do another training epoch where we take some subset of the data to update our network.
Okay. And so the question, I guess, would be, do you have any feeling about sort of how quickly that can happen? Are there situations in which it might not, or conversely, are there situations where the physiology might help you here a little bit? So for example, when we think about things like circadian rhythms or something, where you might expect certain timescales to be involved.
Yeah. So I think one nice thing is the place where I think that things like circadian rhythms can come in and help you is because we're doing this sort of feature extraction rather than using the raw LFP data. I think if you're using the raw data, like I said before, there's a risk of overfit, because if you're only looking at, say you're looking at a 24-hour cycle, right? And you're looking in the first hour, and the only data that you're actually looking at are LFPs that look like the LFPs in that 1 hour time window. But if you're looking at the features instead, I think one of the advantages there is that you can actually learn something about data that you haven't seen yet if it's similar to what you've seen so far. So in this feature space, we might know something about it just from doing this autoencoder. And in fact, we had done a version of this prior where we weren't using an autoencoder, and we were just going straight from the power spectral density of the LFP. And what we found was we had a lot more fluctuations in terms of the performance as we actually varied the parameters. So in that second part where we did the parameter variation, it was a lot less robust or a lot slower to respond effectively to the control that we were doing. So I do think that the feature selection does help with that, where you actually kind of get information about the rhythms just by having sort of general information about being able to identify it in the feature space.
Brilliant. Thanks very much. We have another question here from Corey. I think you're unmuted now. So
yeah, can you hear me?
Yep.
Yeah, Tim, how's it going? I'm just curious if you've considered any other model-free prediction algorithms.
Not specifically. I mean, one reason is that we found that this has worked pretty well, and we think, again, like when we were looking at the real data, I think one challenge was finding kind of efficient benchmarks. So there are some things we still want to look at. Like we want to look at how well things like PCA could work, for example, in
Right.
making these same predictions. So that's something we're still looking to do. But I think we're pretty happy with the results that we're seeing right now in terms of, especially with the control stuff.
Yeah, I just had an idea because I know you co-authored a paper in the Koopman realm. I'm not sure if you're aware, but there has been some recent work in Koopman model predictive controls.
Yes,
like someone like you, that would
I think Koopman can do a lot of things very well. I think that because of kind of the complexity of the data, I'm always a little hesitant about something like Koopman with problems like this. I think that it can do a lot of similar things and it can kind of reach the same endpoint. But one thing I like about doing things like autoencoders compared to doing Koopman is I don't need to have a specific form for like what I want the correct answer to be, I guess. Like I don't really care about actually in this case analyzing specific modes. I don't really care what the primary mode is so much as I want a network that's going to find data that's going to be useful to the specific application that I want. So I think Koopman could do some similar things. I haven't done it with Koopman, obviously, but I think that's kind of my general take on it, I guess, is I think Koopman's very powerful for like dynamic analysis. Here, where we're less specifically concerned with the dynamics and we're more concerned about kind of the effects of those dynamics may be, I think that this approach is a little bit more flexible, I guess, in terms of what it can give us than Koopman.
Thanks for your input.
Brilliant.